you. Okay, so this is a joint work with Chris Hall and Will Sawin, and I wrote the outline. So I will start with some background, and we'll define Ramanujan graphs and tell you about why they are interesting. And then I will state the main result. It's about Ramanujan coverings of graphs, and then I will give a quick overview of the. So I mean, it all started 2 years ago when Marcus Spielman and Srivastava published their breakthrough about Ramanujan 2 coverings, which also showed that there are infinitely many Ramanujan graphs for every degree, and I will explain this. And so I'm going to give an overview of their proof, and then I will explain what are the difficulties in generalizing their proof to general to every 2, so that we can change this 2 to every number. And I will give an overview of our proof, and I will finish with some open problems if there is time. Okay, so I'll start with the Ramanujan graphs, with a background. So what are Ramanujan graphs? So in one word, these are optimal expander graphs. And okay, so I probably should not. So first of all, what are expander graphs? So I will just say very, very briefly because I assume everyone here knows about it. So these are, expander graphs are usually large graphs with few edges, so sparse, but yet high connectivity. And more particularly, this high connectivity can be, so it has several combinatorial meanings. So for example, we don't want to have bottlenecks in the graph. We want a random walk to mix very fast. We want the graph, any 2 subsets of the graph, to have roughly, to have the number of edges between any 2 subsets should be roughly the same as in a random graph. So there are all kinds of combinatorial properties to measure this high connectivity. But the important thing here is that these properties, so this is these properties of high connectivity can be measured by the spectrum of the graph. By spectrum. Of the graph. And what is the, oh, no. Okay, so let's now give the details what I mean by the spectrum. So let's G be a finite graph. A of G is the adjacency matrix. And so the eigenvalues, so the spectrum of G in this talk will be just the eigenvalues of the adjacency matrix. And because the adjacency matrix is symmetric, all the eigenvalues are real. And let's denote them by, let's say that G has n vertices. So the eigenvalues of G will be denoted by lambda 1 up to lambda n. And now let's say that G is also, okay, so let's say that G is, if G is regular, let's say that G is K regular. In this case, lambda 1 is K. Lambda n is at least minus K. And now here, if G is connected, let's also assume that G is connected. If G is connected, lambda 2 is strictly less than lambda 1. And this one, here we have equality if and only if G is bipartite. Okay, and okay, and the fact I wanted to measure, so how do these properties of expansion measured by the spectrum? Simply by the fact that G is a good expander. It can be measured by having lambda 2 and lambda n in absolute value small. So the smaller lambda 2 and lambda n are in absolute value, the better expander G is. And so this is the big picture. So we want to build, so the optimal expanders will be graphs where these two eigenvalues are as small as possible. For the Chigal constant, lambda n is not important. For the other properties, it is. So yeah, some measurements are only depend on lambda 2. Okay, and so we want graphs to have lambda 2 and lambda n as small as possible, but there is a lower bound by Alan Lupana. Did I double the right letters? Double P and one n. Which say that, okay, so probably you also only said for lambda 2, but it's the same proof. Okay, anyway, both these numbers are at least 2 square root of k minus 1, k is their regularity, minus small o of n. Small o of 1. Okay, so this brings us to the following definition by Lubotsky, Philip, and Sarnak, I think, or certainly by Lubotsky, that a graph G is called Ramanujan. If let's say that, so if all the eigenvalues are strictly less than 2 square root of k minus 1, okay, or in other words, it means that all the non-trivial eigenvalues, so lambda 1 is always going to be equal to k, it means that all the non-trivial eigenvalues are inside minus 2 square root of k minus 1 and plus 2 square root of k minus 1. And let me add another definition. We'll say that G is bipartite Ramanujan if so lambda n is equals minus d, which means that it is a bipartite, and all the other eigenvalues. Your degree is k. Yes. Okay. Yeah. It's unfortunate. Yeah, I used d for 2 different things here, and then I decided not to use d at all. And okay, so this is bipartite Ramanujan, and okay, and actually, so I talked here only about regular graphs, but actually everything here works for any graph. Yeah, exactly. So if the graph is bipartite, the eigenvalues are symmetric around 0. I mean, simply because if you have 2 parts of your graph, and you have some eigenfunction, you can take one part and negate it, take all the values and just put a minus sign, and then you get you negate the eigenvalue. Yeah, so before I move on, I just want to say two. So I don't want to spend time on explaining exactly what happens for the non-regular case, but everything I'm going to say works for irregular graphs as well. And just one note is that this number, so where does this number come from? 2 square root of k minus 1. So all the k regular graphs have the same universal covering tree, which is a k regular tree, and this number is simply the spectral radius of this tree. So for other graphs, we can take the universal cover, take the spectral radius of this universal cover, and then we get some number. And if we replace this number by this other number, I can state everything in the same way. Okay. Okay, and I will denote it by rho. Okay, for just I'm going to denote this by rho.
It's a number of a graph or a family of graphs.
It's for graph, and so every graph defines a family. So if you have a finite graph, it has the universal cover, which is let's say in the regular case, you take a k-regular graph. You can build a universal cover, which is just a k-regular tree, and then you look at all the graphs that have the same universal cover. And in the regular case, these are all k-regular graphs. And you have an analog in general. Okay, so let's look at some examples. Oh, this board is very. Can you see? It's not very. Okay, so some examples for k-regular graphs. For Ramanujan graphs. So k plus 1. This is the full, the complete graph on k plus 1 vertices. It is k-regular, and its eigenvalues are exactly minus 1 with multiplicity k and then k. So this is Ramanujan. You can also take a graph with k over 2. So it's a k-regular graph with k over 2 loops. So it has only one eigenvalue, which is k. So it is also Ramanujan. You can take the complete bipartite graph on 2, where the two sides have k vertices. This is the eigenvalues here are minus k, and then zeros and k. So this is bipartite Ramanujan. And you can also take here this graph with two vertices and k edges between them. It has two eigenvalues minus k and k, so it is also bipartite Ramanujan. So it's not hard to come up with many Ramanujan graphs of this sort. But the challenge is the following. It was perhaps stated by Lubotsky. I think in 94. So are there infinitely many Ramanujan graphs? Okay, sorry, k-regular Ramanujan graphs for every k. And you can also ask if there are infinitely many Ramanujan graphs in every family of graphs, which, by the way, is not true, but So, yeah, I'm not obeying to the rule I said. So I don't want. I'm saying that if the generalization of this question to the non-regular case doesn't work. So there are counterexamples of families of graphs where there is no Ramanujan graph. But you can also deal with it with the right definition. You can also deal with these families and still make this question make sense. So in other families there could be more than one bad eigenvalue. In the k-regular case, there's only one bad eigenvalue, which is the k, and there is the general belief that you can't build infinitely many graphs where there is only one bad eigenvalue outside the Ramanujan interval. And in other families, you may need to compromise with several eigenvalues outside the Ramanujan interval, but you can still, but only a finite fixed set. Okay, so this is the question, and here's what is known about this question. So first of all, this is true if k is some prime power plus 1. And these are Cayley graphs. So this is a construction of, this is an explicit construction of Cayley graphs. Of PSO2 or PGL2 over finite fields. And this is due to Lubotsky, Philip, and Sarnak, Margulis, and the most general case by Morgenstern. And there are a few constructions for k equals 3, and so there are a few other constructions for specific values of k, which I'm not going to mention. But the big result in this direction was by Marcus Spielman and Srivastava. And this was first published. They published it in 2013 in Stokes, and then in 2015 in Annals. So there are infinitely many. So yes, for the bipartite case. For bipartite Ramanujan. So they showed that indeed for every degree k, there are infinitely many k-regular bipartite Ramanujan graphs. Okay, but the general question remains open. So, I mean, we still don't know the solution to this problem. And let me just state two more supports for this, why we think this holds, and actually, so two more supports to this conjecture. Okay, so more support. So first of all, so Friedman, this was published in 2008, and Bordenave in 15. I mean, this is a result of Friedman, but there is a new proof of Charles Bordenave. Show that random k-regular graphs are nearly Ramanujan. So it means that if you look at the eigenvalues, instead of being between minus rho and rho, if you add here an epsilon, then already almost every graph falls into this, the eigenvalues fall into this interval. And the second thing is that actually, so the common belief, and this is based on some simulation and some analysis of the simulations, is that actually a constant fraction of graphs, of say k-regular graphs, are Ramanujan. So when the number of vertices tends to infinity, there's a constant. The proportion of Ramanujan graphs, it's believed, should converge to some constant, like 70% or 50%. So it's not. I mean, it depends on your what model exactly you believe, but this is what the simulations suggest. So we are very far. So the really interesting question would be to understand exactly the distribution of the largest non-trivial eigenvalue. This is And so every epsilon, for every positive epsilon, this is true. I mean, when n tends to infinity, almost every graph, the proportion of Ramanujan graphs that fall into this tends to 1. For every epsilon. Yeah.
And this needs little o of 1 to prove the
Here?
conjectures.
No, this is the other direction. This is, so I add epsilon. This is minus epsilon. This is plus epsilon. Yeah. Yeah, so from one side you have a deterministic boundary. From the other side, this only holds in probability. So I would just say that, I mean, so the simulations, so there were a few students of Sarnak, and now there is some other people doing simulations, and this general belief is that the second eigenvalue looks like the distribution is Tracy-Widom type. So like the same distribution that you get from random matrices, I mean GOE or something. Okay, so now I want to go to to describe our result. So I mean, so the idea came from the basic idea to this result, you know, and of course to MSS, Marcus Spielman and Srivastava, came from Jonathan Bilou and Nati Lineal strategy. So the strategy was to construct Ramanujan graphs by a tower of coverings. So here is so let me explain what a cover is. Okay, I need to find a better chalk. So what is an R covering of a graph G? So you start here with a graph. Let's say this is G. And then the covering, which we'll denote by H. So you duplicate every vertex until you have R copies. And here you have V1 up to VR. And then for every edge, you take some perfect matching between these vertices and these vertices. Okay, and then the important thing is that locally, if you look at at every vertex, then if you look at all the neighbors it has, so it has exactly the same neighbors as this guy, only that, I mean, so if this guy has a neighbor here, this guy will have exactly one neighbor that sits above this vertex. And so the good name for this is coverings, because this is this is a topological concept that applies for any topological space. But some people call it lifts, which is a bad name, because in topology it means something different. So we will call it here coverings. So you see an R covering. So to specify an R covering of G, you need is determined by exactly you need one permutation for every edge. One permutation in SR is determined by permutations. Yeah. So I'm going to explain exactly what the strategy is. Yeah, but we'll start with a small graph, which is Ramanujan, and we saw that we have small Ramanujan graphs. That's not a problem. And the idea will be to construct coverings which are still Ramanujan. And then these coverings you can build more coverings which are still Ramanujan. And then you can get a tower of covers. And and this brings me to the following definition. So the definition is of what is a Ramanujan covering. So definition. So H, this is a covering, is a Ramanujan covering. Oh. Wait, before that. Okay, before I define this, so another important property is that the eigenvalues of G, are inherited by H. And why is that? This is because if you take some eigenfunction here, you can simply duplicate it to be an eigenfunction of this graph. Take this value and put the same value on all these vertices. And because this local picture looks the same, if you do this, then if you take this eigenvalue and put it to the covering, it will also be an eigenfunction here with the same eigenvalue. Okay, so we know that, I mean, a part of this, so this is, so we have some eigenvalues of H which are determined by G, and then we only care about the new eigenvalues, and we said that H is a Ramanujan covering if all new eigenvalues are in the Ramanujan interval, and we'll say that it is one-sided Ramanujan covering if all eigenvalues, if new eigenvalues are at most rho. So if you can bound it only from above, the new eigenvalues. And the conjecture of bilineal is that every graph has a Ramanujan 2 covering. So they actually conjecture it for the regular case, but let's take it for any graph, any finite graph.
Friedman conjectured it to the general case.
No, I think he conjectured for random coverings, not for that random coverings are nearly Ramanujan. Not that
For random coverage.
that random coverings are nearly Ramanujan. So this but this is about strict Ramanujan and existence, not.
Doron, when you take this covering, so you get
Yeah.
the same row.
The same what?
The same row.
Yes, because I mean the universal. Yeah, in the regular case it's the same, but also in general you get the same universal cover. Yeah, that's a good point. Yeah, you get you always everything I do doesn't all these actions you stay in the same family of graphs, where a family is defined by universal cover, and one example is the one. So yeah, and you can always think about the family of k-regular graphs. Okay, and so this conjecture again, this is still open, this conjecture, but in this general, in a general sense. But notice that if this conjecture is true, then this leads to Lubotsky's question. I mean, yes to Lubotsky's question. Right? I mean, if every graph has a Ramanujan 2 covering, you can start with say this graph or this graph, take it to covering, and get a graph. Let's say you take this graph, you take a Ramanujan to covering, it means you find a graph with 2 vertices, which is still Ramanujan, because, I mean, all the non-trivial eigenvalues here are Ramanujan, and also all the new eigenvalues are Ramanujan. And then you can go on, build a graph with four vertices, and then 8 vertices, and 16 vertices, and you get an infinite family of Ramanujan graphs, which are k-regular.
Better not to start, because this example is only for even.
Right. Okay. Yeah. So let's start with this with the complete graph. Yeah, you're right. It's a good one. Yeah. So start with the complete graph, and then you even get simple graphs, and not. Yeah. So this is the strategy of bilineal, and so this strategy was partially fulfilled by MSS. Spielman and Srivastava. And they showed that every G has a one-sided Ramanujan covering. Sorry, one-sided Ramanujan 2 covering. Okay, so they were able to control the new eigenvalues only from one side, not from both sides. So they could show that all eigenvalues are at most rho, but not that they are at least minus rho. And now, because of what we say about bipartite graphs, right? You said that bipartite graphs have a symmetric spectrum. So if you start with a bipartite graph, then of course the covering is also bipartite. You still have two sides for the graphs. And then the spectrum is symmetric, so if you can bound the spectrum from one side, you can also bound it from the other side. So this immediately shows that every bipartite G has a Ramanujan 2 covering. So not one-sided, but full Ramanujan covering. And this shows that there are infinitely many k-regular bipartite graphs, bipartite Ramanujan graphs. Okay, again, you start with this graph. Say you start with this graph or with this graph, and then you build a tower of coverings. And you get infinitely many Ramanujan graphs in this family of bipartite k-regular graphs. And it actually, this holds also for any family of graphs, not necessarily Ramanujan. If you have one bipartite Ramanujan graph, you get infinitely many. Okay, because this result holds in general, not just for regular graphs. Okay, so this appeared roughly 2.5 years ago, and so when it appeared, and so I actually gave a talk about it in Jerusalem. They asked me to give a talk about this result, and I thought this. So there were two things that I wanted to that I thought about. First of all, I mean, can you generalize this to, of course, full Ramanujan graphs? So can you use this method to bound the eigenvalues from both sides, not just from one side? And the second thing is, why do we need these two? These two look suspicious. I mean, 2 is not a special number. There shouldn't be. So, and the first, so I still don't know how to, I mean, we still don't know how to solve the first problem of generalizing these two Ramanujan graphs to full Ramanujan graphs, not just bipartite. But we could get rid of these two. And this is the main theorem I want to discuss. So this is with Chris Hall and with Sawin. So this works for everything. Which which means that every G has a one-sided Ramanujan R covering for every R. Which of course means that so every bipartite G has a Ramanujan covering, a full Ramanujan covering, Ramanujan R covering for every R. And so let me speak. I want to say a few words about why this is interesting. Why this result is interesting. So first of all, I mean, so I think it gives a better understanding of the result of MSS. I mean, because as I said, I mean, it looks suspicious that there is this 2. I mean, why should there be something special about 2? So I think it gives a better understanding of the result. And secondly, it gives some new Ramanujan graphs, so more Ramanujan graphs than we knew before. Or in other words, the family of Ramanujan graphs which we can construct is larger. And third, it gives some ideas or some, it opens some questions. The method of proof opens questions about fast construction of Ramanujan graphs. And I will talk about it at the very end. Okay, so now I want to move on to show you to explain to give an overview of the proof of MSS. So there are 3 main ideas in this proof. Okay. So now Ramanujan two coverings on MSS. So there are 3 main ideas. One, okay, so I'll just give the titles and then I will explain the details. So the first idea is to not only look at the discrete problem of discrete coverings. So we don't want to decide for every edge. So in general, okay, what is a 2 covering? A 2 covering, if this is G and this is H, then you have 2 vertices above every vertex. And now for every edge, you have 2 choices. You need to choose either to pair the edges like this or to pair the edges like this. Okay, you have only 2 options. And now let's say we don't want to make a full decision whether we want this case or the other one, but we are willing to take some probability to make it random and just specify some probability P for every edge, which will say that yeah, in probability P we take one of them, in probability 1 minus P we take the other, and so they show that the average. Okay, so there is the variables are independent and the probabilities are arbitrary. So you can put a different you can put a different probability in every edge, and these are independent. But this is important just because of this result that these are real-rooted areas in the let's say in the simplex of probabilities of distributions of coverings. So I will explain exactly what I mean by real rooted and etc. And then the second thing is to, in this area, find the Ramanujan point. In this area. And the third part is the method of interlacing polynomials. Okay, so to define it, I mean, so to explain these three ideas, it is better to first do a zero stage, which is not important, but it makes things easier, which is a change of basis. Okay, so now let me explain. Okay, so first of all, what do I mean by change of basis? So this is just, again, for convenience. So remember that, what is the, so H is this 2 covering of G. So what is the adjacency matrix? Let's say we put here U1 and U2. And here we have V1 and V2. So in general, we have 2n vertices here. I mean, 2n vertices over 2n vertices. So here we have a small square. And here we put either the identity matrix if we have these options, or we have this other permutation, 2x2 permutation matrix if we have this option. This is the adjacency matrix of H. But now let's make a change of basis where instead of say we take the, so here the basis for this matrix is, instead of taking this basis, we take this basis. And let's also change the, okay. And then with the new basis, this is of course still the identity, but this guy becomes 1 and minus 1 with the new basis. And now we can change the order of lines and columns. And what we get here is that if we take all the first we take these elements of basis, and only then we take this guy, then we see that here we actually just get 1 in this corner. We just get 1 whenever we have an edge in G. So we actually get here the adjacency matrix of G. And here we get, so we got here 1 and minus 1, right, in these two examples. And this is just, so this is actually, I will denote it by A sign, because this is the sign of the permutation. And this is very convenient, because remember that the eigenvalues of H consist of the old eigenvalues and the new ones. These are the old eigenvalues. These are the new eigenvalues. So now we actually need to study this. Okay, so the goal is find signing of edges of G such that the spectrum of this sign matrix is inside the Ramanujan interval. Okay, so now so this is the first, the zero stage, which is just for convenience. And now what do I mean by these real-rooted areas? So the idea is now to take convex combinations of coverings. and the particular, and now let's focus on this case. So on these probabilities. So again, we take, for every edge, we take some probability, and every edge is independent. And then, so what MSS showed is that if you take the expected value of this over this probability, so again, we take an independent probability for every edge of, and we want to look at the spectrum of this matrix, which is okay. So what we have here, I mean, so we want to show that we want to show that I mean, to show that the spectrum of this matrix is inside the Ramanujan interval, it means that all the roots of the characteristic polynomial are here. And what they showed is that if you take these combinations, these convex combinations of probabilities, you get, not that this is Ramanujan, obvious. Of course, it cannot be always Ramanujan, but it is real-rooted. Which is highly non-trivial. I mean, here the eigenvalues are here. The spectrum is real-rooted because it's a symmetric matrix. But once you start taking, but here you take combination. I mean, here you take average of polynomials, average of characteristic polynomials. There is no reason for this average to be real-rooted. So this is the main technical result of MSS, and let me just make one point here, just to give this, so you can think about it as, let's say we have two edges. If we have two edges in G, so we have one probability for each one of them. So this gives us a square. We fix one. We have here P1 and P2, and every point, this defines a polynomial which they show is real-rooted. But if you think about it really as in the convex hull of all possible distributions, it should look like that. I mean, if there are two edges, you have, I mean, this is just, here is these are the choices for the two edges. You have two possible choices for every edge. So this is really the simplex of possible distributions of coverings. And what this cube represents is this line, this line, this line, and this line. And then you take some, I mean, I don't know how to draw it. You connect these two lines by straight lines all over. So you get some, so you should think of this is a cube, but actually in the simplex of probabilities of distributions, this cube is embedded in this strange way. Can you see that? No.
So basically, for every edge, you give it a sign of plus or minus with the probability P1, P2.
Yeah, I mean P1 for one edge and P2 for
one
for the other edge.
And you want to look at this. Now you want to look at the average of or it's a characteristic polynomial.
So you look at the average of characteristic polynomials. So it's actually an average. So I have four different. If I have two edges, there are four different. Characteristic polynomials. I mean, four different. Or in general, if I have m edges, I will have 2 to the m polynomials, and I look at some averages. But I mean, this is the real so the simplex of dimension 2m minus 1. So with 2 to the m vertices, this is the real simplex of possible convex combinations of these polynomials. But this I have 1 point so but P1 and P2 gives me 1 point. But in general, this family where I go over all P1s and P2s. No, I don't want to average. I'm just saying that when a group of homomorphism from gamma to GL, let's say K. It's not the same K as before. C. And yes. Yeah, I will need only for the symmetric group, actually. Yeah, so you can think of, yeah, so in the paper we say something a bit more general, but about other groups, but let's say, you can think of gamma as a symmetric group, even S3, because we only talk about 3 coverings, or S4, for 4 coverings. And now we say that pi 1 and pi 2 are isomorphic, if and only if there is some matrix B such that, I mean, that you can get one by simply conjugating the other by a fixed matrix. This is for every G in gamma. So this is what we mean by isomorphic representations. The sum of 2 representations is simply defined by taking, if this is K1, if this is K1, this is dimension K1, GL K1C, and this is K2, this will be a K1 plus K2 dimensional representation, and you just put here pi 1 of G, and here pi 2 of G. So you get a homomorphism into GL K1 plus K2. The trivial representation from gamma to GL1C, which is just C. This just maps every element to 1. And finally, but very importantly, an irreducible representation. So pi is called irreducible if it is not isomorphic to a sum of representations. So you cannot decompose it like that as a sum of 2 representations. I will soon give an example. I will soon exemplify this for S3. Okay, so here are some classical facts. I mean, up to now it was just definition. So first of all, every gamma, so every finite group has only finitely many irreducible representations. So let's say, let's look at S3. So S3 has only 3 irreducible representations. This is one of them. Okay, so what we know, what I denoted by standard, this is just one of them. And there are 2 others. So of course we have the trivial representation, which just gives 1 to each one of them. And we have the sign representation. These 3 permutations are even, and these 3 are odd. So these are the 3 representations, irreducible representations of S3. Okay, and by the way, I mean, if you look at, and the change of basis we did before is actually the fact that if you take the trivial representation plus the standard representation, you just get the permutation representation. So just in this case, if you take this plus this, you actually get something that is isomorphic to just the usual thing where you take a permutation and construct a permutation matrix. And the second facts, so these facts are from the beginning of the 20th century, or the end of the 19th century. This is Frobenius and Burnside, and perhaps Schur. And the second thing is that every representation of gamma is a sum of irreducible permutation, and this is uniquely. So there is only one decomposition up to the order, and this is the important result that we want to use. So I'm not sure this should be assigned to Peter-Weyl, because they have done it for, it was probably known before for finite groups. By whom? I couldn't find. They knew it? Yes. What I'm going to say? Okay. Okay. So for Frobenius, sure. Okay. Some theorem from the beginning of the 20th century is that if pi 1 up to pi L are the irreducible representation of gamma, then their matrix coefficients are orthogonal, are an orthogonal basis, actually, for all the functions from gamma to C. Okay, so you can see here. I mean, this is a group. SV is a group of size 6. So this is a 6-dimensional vector, and we actually have we indeed have 6 matrix coefficients, right? We have 4 here and 1 here and 1 here. And if you look at the values, you will see that they are all orthogonal. For example, this matrix coefficient is orthogonal, say, to this matrix, this matrix coefficient. Okay, I mean this is easy, but also yeah, you can check every 2 of them are orthogonal. I mean, every 2 different are orthogonal, and it also gives you and you can also know the exact value of. So the exact value, if you take the same vector, the value will be exactly G over. Okay, perhaps I will say it. So I'll just say it. I'll write it explicitly. So you look at this summation. So you look at pi I, one of the representation of G, in the JK position. You multiply it by pi I prime of G in the J prime, K prime positions. Then this means that if I equals I prime, J equals J prime, and K equals K prime, so if you have chosen the same thing, okay, this has to be like that, then you get G over the dimension of pi I, and otherwise you get 0. Okay, let's look at one example here so if we take this, the green ones, times themselves, we get here, since each one of these is on the unit circle, we actually get just 3. The sum is going to be 3, and this is indeed 6 divided by 2. So now we'll use this, and So now we'll use this and go back to ASTD. So remember that what we want to show is that the uniform distribution gives you a Ramanujan point. So let's go back to ASTD. So remember that it's some matrix with two on two blocks. And every block looks like that. But we want to show that if we take the average, so we want to show that the average over uniform distribution over signings. So these are distributions of labeling of S3 labelings of G is, and you take the determinant, the characteristic polynomial of A of this matrix, then it is Ramanujan. This is the goal. Okay, so let's this is why this is the point where I wanted to show beforehand the proof about the matching polynomial in the R equals 2 case. But what are the difficulties here? I mean, so the point is that this is a determinant, so you can go over all diagonals. What is the word in English for אלכסון מוכלל? General diagonal? Okay. So over all general diagonals, this is, you take the sum and you take the expectation. Now, when you take, when you take this uniform distribution, of course, every block is independent of another block, right? Except for these two blocks. I mean, if you take two symmetric blocks, so these are, if this is the ij and this is ji, so these two blocks are dependent because this is just, here you have standard of sigma and here you have standard of sigma inverse. But any other combination of blocks, I mean, any two other blocks are independent because the uniform distribution, you take this, the labeling of every edge is independent of another. And now let's take, now we go over all generalized diagonals. So let's say we take, some diagonal, let's say we have 1 point here and 2 points here and some other points. So this is some generalized diagonal. And what you take is you take the expectation of the product of all these green points, and you can, of course, I mean, because this is independent with the other ones, you can break it into small powers, into small products, where each time you just collect the points here together with the points here. Okay, so the goal is actually to think about what happens when you take several points here and several points here and take the product. What is the expectation of this? And okay, so one thing we have, and if you do this for the R equals 2 case, this is just an exercise, you get a matching polynomial. Now, the problem here is that, okay, how do you, I mean, we don't know anything about the product of these two guys and these two guys.
Because all the other terms cancel.
You know what, perhaps it will be, perhaps it's worth perhaps I should say something about the R equals 2 case, because this is too, perhaps, abstract. So in the R equals 2 case, so I just have here, so in every point here I have a plus minus 1, And here I have also a plus minus 1, but this is the same plus or minus. Here I also have plus minus 1, but this is independent of this guy. Now, for every generalized, if, for example, my generalized diagonal contains this point but does not contain this point, then because because the average here is 0, this is the whole diagonal is 0. So only when I take this point and this point. So I have to take them in pairs, and of course I can put things on a diagonal because these are the x's. It's not the determinant of this matrix, but the characteristic polynomial. So the determinant of xi minus the matrix. So it means that I can actually count. So these are only permutations. The permutations I get here are just involutions. And it turns out that I count exactly the matchings of the graph. But here, it's not just matchings because I can have more points in every block. So the first idea is to.
But again, you need terms that from every pair of disjoint of symmetric things, they will contain something from both. Right? Because things will fall. Terms that do not.
It's not clear. I mean, if I have three points here, and okay, here I can't have 3 because it's 2 by 2. But in general, if I have 3 points here and none here, I mean, if I have 2 points, then because of this Peter-Weyl theorem,
But if you have many.
and also if I have 1 point, but if I have more than. Okay, it's not clear. And even if you have 2 of each, what do you do then? So first of all, one idea is first to group together all generalized diagonals which fall to the same minors in each block. So I group together. Let's say I look at all the permutations such that in this block there is only 1 point, and in this block I have either this or this. But anyway, it defines the same minor. So I use the same columns and rows in every block. So here I just use this one. Here I just use this one. And now there is a way. I don't have much time, so I will rush a bit. So there is a way to present, so I group together all the generalized diagonals that for each block, in each block use the same columns and the same rows of the block. And then there is a way, this is just technical, to write this expression as an expression that depends on these minors. So I actually get, if I do it together, I get actually the determinant of this guy. It will be dependent on the determinant of this guy times the determinant of this minor. Okay, so I get, I can express, let's say this. Sorry, we denote this by, so this expectation by some expression involving. So what I have is an expectation over. So I have one minor, some minor of ij block times some minor. So when I mean minor, I mean the determinant of the minor. Some minor of ji block. So what I mean is that I have, this is the only case, this is the only places I have expectations. Except for this, I multiply them and sum them, but this is the only case where this is the only place where I actually have expectations. And now, what is the meaning of these minors? So this is another nice thing from representations. So what is the meaning of minors? If you don't ask Donald Trump, you can get, you can see that the minors, so in one word, these are the exterior exterior powers of STD, of this representation. And what do I mean? So I have this representation, STD, it acts on a, so I can think of it as my group S3. It gives me a way to act, or it gives me matrices in 2x2 matrices. So let's say that this has basis V1 and V2. This is the basis for C squared, for C squared. And now the exterior powers is the way I can get from this some kind of this of action of S3 on yeah, here is just the determinant, but in general there is a space. If you have some space, let's say C to the R, there is, I can derive from it a space C to the, let's say, R over 2, which is defined by taking, which such that the basis for this is all the pairs of basis elements. So this is R over 2. And the action, so, and this I can define if I have, in general, if I have an homomorphism from gamma to GL RC, I can get a representation from gamma to GL R over 2C. And what does it do for this? For this basis element, it will just, it will act, I just need to take this action on VI and this action on VJ, and then see how I can decompose it with this basis. So okay, this is what's very fast, and if you didn't know it before, you probably can't understand it right now. But it turns out that these minors, a minor of a representation is exactly gives you the matrix coefficient of this representation. So if you take all the 2x2 matrix, all the 2x2 minors of this matrix, how many minors do you have? You need to choose. You have. Yeah, I mean the number of minors, you have to choose two columns times two rows, and this is exactly the size of this matrix, right? R over 2 squared. So these minors are exactly correspond to the exterior powers of STD, and this is another fact, which is also quite classical, is that the exterior powers of STD, so the standard representation of the symmetric group. So you can think about this case. So we have the so you take the permutation. Yeah, you have the natural representation of symmetric group, which is just every permutation construct a permutation matrix, and then you take out the trivial representation, which is always there. You get an R-1 representation, which is irreducible, and this is what I call the standard. So the exterior powers of STD. So we have of STD, which is let's say from SR. So in general, the standard representation takes S is an R-1 dimensional representation of SR. So we have, if you think about it, okay, we have R different powers. We have the zero power, the 1 power, up to the R power, up to the R-1 power, are all. So these all representations are all irreducible. and different and non-isomorphic. Okay, so in this case, for example, this is the standard representation. So the trivial, the zero exterior power, the minor of the empty set, you get the trivial. So this is, in this case, this is going to be, you always get the zero exterior power is always the trivial one. Okay, the first exterior power just leaves you at the same place. And what is the second exterior power? So, I mean, in this case, it is represented by all 2 by 2 minors. So you have just one, which is the determinant. If you take the determinant of each one of them, you can see that the determinant here, here, and here is 1. And here, here, and here, it's -1. So you see that this one, this guy, is the second power. And this is going to be in general. I mean, you will not always get all representations. But, but you will get always, but all these representations will be different and irreducible and non-isomorphic. And this will exactly enable me to compute this thing. Yeah. This thing, because now, I mean, these are exactly matrix coefficients, and my Peter-Weyl theorem, we know their values. And we know that actually we had to pick, so it means that to get something that is non-zero, we had to pick the same minor, the exact same minor in here and here. We have to be, actually it should be the symmetric power, the symmetric minor, because this is sigma and this is sigma inverse. But for every minor here, we can choose only one specific minor here, and then we also know the exact value. And okay, without giving the details, I'll finish by stating so what is the answer? What is this? What do we get here? How do we show that it is Ramanujan? Okay, so this is also a nice result by itself, I think. So remember what happens for the R equal 2 case. If you take the uniform distribution, you get the matching polynomial. What do we get here? So this is if you take this, so this thing, where is my ping? So this average of characteristic polynomial is the expectation over all 2 coverings of G of the matching polynomial. Or H is a 2 covering of G of the matching polynomial. So I start.
You start at, now this is, we are talking about general R now?
Okay, I know. So this is R minus 1. So if you want to construct R coverings, so actually the zero phase, what we did was actually we looked at the standard representation, which is R minus 1 dimensional, and we also get R minus 1 covering. So if R equals 2, you get here the average over all 1 coverings of G, which is just G, so you get the matching polynomial. In general, you get the average of all matching polynomials of all the 2 coverings, of all the R minus 1 coverings. And the point, and the crux is that you know by Hellman-Lieb that each one of these polynomials, each one of them has all the roots inside the Ramanujan interval of the family. And now you take some sum of them, but you know that, I mean, if this is the Ramanujan interval, you know that all these things are positive here. All these matching polynomials are positive here, and all these matching polynomials are either all of them are positive or all of them are negative. It depends only on some parity thing that depends on G and R. But it's going to be the same sign here and the same sign here. So here you will never have roots here in the average. You will never have roots here. So if you have real roots, they will fall here. And by MSS, we know that you have real roots. We have only real roots, so this is actually a Ramanujan point.